All right, in this video, we're going to start our study on Unit 2, which is going to be all about derivatives. So we're going to start off with something that's going to come up quite a bit, and it's this idea of the average rate of change. And it's probably something you remember from your Algebra 1 days. So just think for a second, what do you remember about the average rate of change of a function? Or just in general, what's the average rate of change? So we want to say, what is the average rate of change of the function f of x over a certain little interval? And you might remember, I'm going to draw a little line. It's just a random linear equation. And the average rate of change was like the change in y over the change in x, or the slope. And we had something called the slope formula that helped you find out what that was. What the average rate of change was. So our average rate of change, what we're going to say is AROC, A-R-O-C, the average rate of change, is equal to the y value at the endpoints, the difference in those. So f of b is just the y value that goes with the x value of b, and f of a is the y value that goes with the x value of a, over b minus a. So that's just your average rate of change, your difference in y's over the difference in x's. And the average rate of change tells us the slope of the line through the points a comma f of a, and that's just the point an x and a y, and b f of b. So we can find the average rate of change on an interval. So that a and b could be any numbers. It could be really large interval, or it could be a real small interval. And that's where we're going to start tying in that idea of local linearity that we talked about last class. So it says find the average rate of change of the function, of the following functions, over the intervals, or over the interval -1 to 3. So just from -1 to 3, what is the average rate of change? All right, so for this graph, I mean, it looks something like, I don't even want to draw that. It's a square root function, right? Looks kind of like that. So without actually doing any work, I know the average rate of change is always going to be positive, right? But what is it going to be over the interval -1 to 3? What is the slope at any point on average over that whole interval? So the way the interval changes, that'll affect your average rate of change. But what I need to do here is I need to find f of -1. So just plug in -1 for your f function. I'm going to plug in -1 for x, -1 times 2, -2, plus 3, that's just 1, the square root of 1, which is 1. Also, I need to write a is -1, b is equal to 3. F of 3 times 2 is 6, plus 3, that's the square root of 9, which is 3. So the average rate of change, I'm going to abbreviate that and use AROC. We're going to do this a lot. The average rate of change would be f of 3 minus f of -1 over 3 minus a -1. Now we're going to clean that up. We're going to say this is 3 minus 1 over 3 plus 1, which is 2 over 4, which is 1/2. Now on the AP exam, on the free response, we would just leave it right there. Actually, we could leave it right here. And we'll talk more about where you can leave it off, but anywhere you can just stop, you're going to get full credit if you leave it right there, which is kind of nice. You make mistakes. There's a possible to make a mistake here. There's possible to make a mistake there. So the general rule is if you can plug it into your calculator and get the answer, just leave it. So if this was a free response question, you would just leave it and you would get full credit right there. But a lot of these are going to be questions on the multiple choice, which you need to actually simplify. But this is an FRQ, and we're going to call this a safe stop. You are safe to stop right there. You get full credit. All right. That'll become second nature later. You're like, what? When do I know when to stop? You'll get it. Just throwing it out there for now. So start thinking about it. All right. So what is the average rate of change of this graph that we have from -1 to 3? So from -1 to 3. Now the interval I said changes what the average rate of change would be, right? So all these slopes right there were negative. Looks right there when x is 0 is 0. And then they turn positive for a while. So we want to say on average over that interval, what is the average rate of change? And you might probably guess it's going to be a positive number. On average, it looks like the slopes are more positive than they are negative more of the time. So from here to here, it would probably even out and get 0. That's the average rate of change would be 0 there. But there's all these extra positive ones. So I'm thinking the average rate of change is going to be positive. And let's see. So the average rate of change gives you the slope on average on that interval. So what is the slope at, average rate of change is f of 3 minus f of 1, that's really hard to read, that's ugly, over 3 minus a -1, which would be plus. So we plug in those. F of 3, looks like it's 8. F of -1, looks like it's 0. So this would be average rate of change. Safe stop right here, but if we're going to reduce, we would say 2. All right, so it's a positive number. That's what we were guessing. More often than not, it looks like the slopes were positive, like all over here. So it kind of averages to be about 2. It's not always 2, but on average, the instantaneous rate of change, the average rate of change, the average slopes at any given point would be 2. All right, let's talk about the instantaneous rate of change. This was that whole local linearity idea. So at an instant, what is the rate of change? What is the slope? Now, if I just had a linear equation, that's easy. Instantaneous rate of change is whatever the slope is at this point, at this point, at this point, and those are all the same because it's linear, right? So if I want to say what's the instantaneous rate of change at that point of the function at that point, well, if I zoomed in enough, I could get it to be completely straight, and I can estimate, right? That's what we did last class. All right, so let's fill out our little thing. So the instantaneous rate of change of a function at a point is defined as the slope of the tangent line. Remember, tangent line touches at one instant, but never again. At a b. A comma b. All right, so if I wanted to find the instantaneous rate of change of that line or that function, almost like a cubic function, at the point -2, 0, or just when x is -2. A lot of times we just say the x number. I would just draw a straight line as close as I could. That's what it looks like, and I would just estimate what the slope is. My rise is 1, 2, 3, maybe like 3 over 1. So a rough estimate would be 3. The instantaneous rate of change at this point, I can say when x is equal to, looks like 0.4. I don't know the y number that goes there. Maybe it's -1. I'm just estimating. Oh, I picked a hard one. That's something we'll learn later. Maybe it's like this. Or maybe it could have been over here. I picked a really kind of hard one to pick. If I picked it right here, a little bit easier. I know that tangent line is going to be below the curve, which just ties in a lot of things about what we'll be talking about soon, which is exciting. So that might be the slope there. Looks like it's a negative slope, pretty steep. The slope right here at this x number looks like it's perfectly 0. So a function can have different instantaneous rate of changes at an instant, at a point. All right, what are we doing here? How can we find the instantaneous rate of change of the point x equals -2? Okay, this is what I just did. we're going to draw the dot at -2 when x is -2. And we're going to use that point. So I'm going to write it out. If you want to write this down, you can. You don't have to. Use the point -2, 0, and a straight edge, like a ruler, or just any straight edge that you have. Make a tangent line that includes a coordinate that you can find. Oops. So this is kind of hard to demonstrate, but if you had like a straight edge, we could kind of like, I could say, okay, well, it looks like it goes through that right there. It may not be perfect, but this is just an approximation. And those are 2 coordinates. It goes right through like a nice, pretty line. And I could say it goes 1, 2, 3. It goes up 2. That's my change in y. And then it goes to the right 1. That's my change in x. So my slope, I can count my rise and my run, or I could even use that little thing we just did. This is the point -1, 3. This is the point -2, 0. And the slope, which is equal to the average rated, no, I'm not going to say that. 3 minus 0 over -2 minus a -1, which would be 3 over, what did I do wrong here? This is embarrassing. What's going on? Did I switch them up? Okay, so I switched up these bottom ones. So this is the one I said was like the first point, so that needs to go first. -1 plus 2, which was 1, so that's point 3. Now, if you use a different point, maybe if you use the point -1, 4, maybe that's better. Yeah, I think that one's actually probably better. The red one looks like it crossed through pretty good. It's going to kind of cross through my line. Let's try the point. If you get the idea, that's great. You just go ahead and move on, but I'm kind of being a little extra. So maybe if I use that point, maybe that would be better. That looks better. I like that one better. Now this is an approximation, so I could say this one's the slope. That's the point -1, 4. That's the point -2, 0. That's 4 minus 0 over -1 plus 2. And now I'm getting that's going to be 4 over 1. So it gets 4. So it's an approximation. But the idea, though, is that's the slope at that instant. Right now, it's not going to be perfect. We're going to find what it is, how it's going to be perfect very soon. All right, that's going to wrap it up for this video. In the next one, we're going to tie in limits and kind of start really seeing what a derivative is. I'm going to stop it here so that the video doesn't cut off.